So, these days we are discussing the subject of parametric curves. So, we started with Hermite curve, which is basically an interpolation curve. Then in the last lecture we looked at Bezier curve, which is one of the approximation curves. Now, in today's class we will take up the subject of B-spline curves and look at what is the importance of this curve and what advantages these class of curves offer over Bezier curves, and also we will extend the definition of B-spline curves to define what we call as a non-uniform rational B-splines or NURBS curve. Now, if you really recall what we discussed in Bezier curve is that one of the problems with Bezier curves is if I want to define, let us say, a curve using, let us say, a certain control points, its order is fixed. Suppose if I take, let us say, 4 control points, then I have a cubic Bezier curve. If I go for, let us say, a 5 control points, then I have a quartic curve, and so on. Suppose if I have, let us say, I have 10 control points which are used to define a Bezier curve, then I also have terms like 1 minus u to the power of 9 and others. Okay. Now, this actually poses problems. Particularly, we have also seen that suppose if I want to find out intersections, or if I want to do any of the numerical calculation related to the curves, you have to basically deal with polynomials which have degrees like u to the power of 9, etc., which is a disadvantage. Ideally, we really do not want the terms like u to the power of 9 or higher order. We have also seen that if I have a cubic, that is, let us say, u to the power of cube, that serves the purpose of most of my applications, because it gives me both slope continuity as well as curvature continuity, and beyond that is not of much importance. So, there was an attempt to define, let us say, a class of curves where suppose if I have a large number of points, control points, but I should be able to still define a curve of whatever order which I want. Let us say, if I want a cubic, I should be able to get cubic, or if I want, let us say, one order lower, I have only a quadratic terms related to u, I should be able to define. So, B-spline curves are basically a part of this attempt, where given a set of control points, the order which I choose for the curve is independent of the control points. I may be using, let us say, 10 points or 100 points or 25 points as my control points, but I have a freedom to basically fix whether I want a curve which is quadratic or cubic or higher order as and when they are required. Now, let us look at how can one go about doing this particular thing. Like here, the curve is again defined by n plus 1 control points. We have seen this in Bezier curves too, it goes from like point p0 to p1 all the way up to pn, since you are including 0. So, these are n plus 1 control points, but you do not specify any order which is fixed by the number of control points. But in the case of B-spline curves, I have to separately give what is the value of k. K is a common symbol which is used to represent the order of a curve. If I take, let us say, k is equal to 4, then I will have a terms like u cube. So, a cubic basically corresponds to k is equal to 4. If I choose, let us say, k is equal to 3, then that means I have the terms like u square, that is the maximum degree of polynomial which we have. Or if I choose, let us say, k is equal to 2, then this is basically a linear, okay, it is in u, and I can also have k is equal to 1, which is nothing but the specific points, okay, you do not have any curve kind of a thing. So, I can also go for higher order, like if I choose, let us say, k is equal to 5, I can also get a B-spline curve which has terms like u to the power of 4. So, it gives you a freedom to choose whatever is the degree of the curve which you want to do that. Now, another advantage of this curve which is shown here is that it has a local propagation. Like when we discussed about Bezier curves, we have seen that if I am using let us say n plus 1 control point, changing any control point will change the entire shape of the curve, because every point on the curve is defined by all the control points. Okay. So, since you have this is called as a global propagation for of the curve, whereas here the curve is divided into number of segments. Okay. In fact, a B-spline curve is not a single curve, you can call it as a composite curve, number of curves which are consisting in terms of segments, but they all meet the continuity requirements. Like suppose if I choose let us say k is equal to 4, which is my cubic, they will all have a continuity which is like C2 continuity, that means slope and curvature will be continuous, but still the curve is in terms of segments. Now, the advantage of defining a curve in terms of segments is that a particular segment of a curve is influenced only by a certain control points. So, if I change let us say any one of the control points, I may have a B-spline curve which is defined by 10 control points and k is equal to let us say 4. If I let us say change one of the control point, then only some portion of the curve, only a few you can say pieces of the curve, few segments of the curve, they are influenced. Okay. That is a major advantage of this particular curve, the one why this is used. And as we discussed in the case of Bezier curves, that I can define both closed curve as well as open curves. If I have a control point, that is starting control point is same as the end control point, then I can also use the definition to define the closed curve. This is true with B-spline curves. Now, let us look at how does this class of curve differs from let us say a Bezier curve. We have already discussed about Bezier curve, this definition we have seen. If I have n control points, then let us say an x coordinate of the curve is given by the binomial coefficient. Okay. It is basically a summation of number of terms, where I have as many terms as there are number of points. Each of these x coordinates will have some influence, and this is actually multiplied by the two terms. You have 1 minus u to the power of n minus I and u to the power of I, and I have a binomial coefficient which is NCI. So, a term expression like this, suppose if I have a 10 control points, I will have a 10 terms here, they will all participating in the definition of a curve, and the parameter range varies from 0 to 1. So, if u is equal to 1 corresponds to the last control point or the last point, similarly u is equal to 0 corresponds to the starting point. Now, let us come to B-spline curve. You have a definition, if you see here. Now, suppose if I have let us say n control points, okay, just like we have the n control points which are participating here in the case of Bezier curve, same thing happens in the case of B-spline curve too, but this function, okay, like this particular function which we have seen in the case of Bezier, which includes NCI 1 minus u to the power of n minus I into u to the power of I, is called as a Bezier basis function. Okay. There is a name which is given to that, it is called as a Bezier basis function. Nik, which is shown here, which is also a function of u, is called as a B-spline basis function. Okay. The definition of this is different from that of a Bezier B-spline Bezier basis function. Another difference which you will see in the case of the definition of this particular curve is that parameter range is not from 0 to 1. Depending on how many control points which I choose, and depending on what is the value of k which I choose, I will have a different parameter range. Take for example, if I have let us say n is equal to 6, that means I have 7 control points. Let us say I choose k is equal to 3. Okay. So, if I choose n is equal to 6 and k is equal to 3, what is the range of u? So, this is n minus k plus 2. So, this is 6 minus 3, that is plus 2. So, that is 5. So, there are 5 segments of the curve. The first segment goes from u is equal to 0 to 1, second one has a parameter range which is u is equal to 1 to 2, third has 2 to 3, and so on. We have about 5 segments of the curve which will define the complete curve. And what usually happens is, we see here that all the control points are participating. Then how does like the local propagation happens is, for a given range of u, many of these basis functions will become 0. Okay, only some of the basis functions are non-zero, and hence the influence is basically restricted to a local in terms of control points. Now, let us look at this maybe through an example. Okay, like I have put down a curve here. So, what you see here is n is equal to 6. Okay, n is equal to 6 means 0 to 6. I have 7 control points which are shown here as P0, P1, P2, P3, P4, P5 and P6. The curve also shows, like if you see these points which are shown here as orange points, they basically represent the curve segments. For example, I have the first curve segment which is this, the second curve segment which goes from u is equal to 1 to u is equal to 2 is this segment, then I have the third segment, fourth and 5. So, when I said n is equal to 6 and k is equal to 3, n minus k plus 2 is basically 5. So, I have 5 segments of the curve which are influenced. So, that is what is exactly shown here. Now, coming back to this, let us look at what are the points which really influence. Like if I take a curve segment like this, the first segment which goes from u is equal to 0 to u is equal to 1, this portion of the curve is influenced by only the k points, whatever is the k which I am choosing. K here is 3. So, this portion of the curve, the first portion, is completely defined by the points P0, P1 and P2. Whatever are the coordinates of P3, P4, P5 and P6 has no influence on this portion of the curve. Now, when I go to the second portion of the curve, that is when I have u which is ranging from 1 to 2, the control points which are affecting are P1, P2 and P3, whereas P0 has no effect on the curve. Neither the points like P4, P5 and P6 have any influence on the curve. Okay. Suppose if I choose, let us say k is equal to 4, then the influence is restricted to 4 control points on any segment of this particular curve. Now, because of this, since the definition is in terms of segments which constitute a composite curve, suppose if I change, let us say control point which is like P5, it will affect a few segments, but it will not affect, let us say, a segment which is going from u is equal to 0 to u is equal to 1. You will also see here that I have put the word non-uniform. So, there are like when it comes to B-spline curve, I can always define in two ways, one which I call as a uniform B-spline curve and another is a non-uniform B-spline curve. The most common form is non-uniform. Okay. Why the word non-uniform which is coming here? Now, this is basically because we know that every segment is influenced by 3 points. Okay. That is, if k is equal to 3, every segment is influenced by the 3 control points. Now, if look from the reverse point of view, like if I take a control point, how many segments a control point influences? It is not the same for all the control points. For example, if I take P0, P0 is a control point which influences only the first portion. That means, it has influence only on between u is equal to 0, u is equal to 1. Take for example, the control point P1. P1 will influence 2 segments which goes from 0 to 1 and then u is equal to 1 to 2. These 2 segments are influenced by P1. Take P2. P2 has influence on 3 segments. okay, it has influence on 3 segments. What about P3? P3 also has on 3 segments. P4 also has influence on 3 segments, whereas P5 has influence on only 2 segments and P6 has influences only 1 segment. Since the influences which different control points is not uniform, so you call it as a non-uniform B-spline curve. Now, why this is done is, if I choose let us say uniform B-spline curve, okay, let us say the same type of functions for all the segments, then curve does not pass through the first and last points. If I want curve to pass through, which is a more common option which is required, if I want to force the curve to pass through let us say first and last control points, then I have to go for this non-uniform nature of the basis functions. That is why the word non-uniform which comes here, which is like the most common version of the B-spline curve which is used. And as we said, I can always choose the value of k to define whatever is the order. In this entire curve, as I go from let us say the first point, starting point of the curve, which is P0, to the last point of the curve, which is P6, during the entire curve you have a slope continuity. Okay. Every curve has a we have discussed about the continuity, like you have something called as, if there is a curvature continuity, you call as a C2 continuous. If it is a slope continuity, you call it as C1 continuity. If there is also a C0 continuity, when all the points are connected with no breaks as far as the curves is concerned. K itself defines what is the continuity of the curve. K minus 2 is the continuity which you have. For example, here k is equal to 3, so k minus 2 will be 1, so the curve is C1 continuity. C1 continuous means there is a slope continuity during the entire curve. So, I cannot expect a curvature continuity in this particular curve. If I want curvature continuity, then I will go and maybe select k is equal to 4, then I have a different definition and hence the curve is. So, the most common option also which is used as far as B-spline curves is concerned is also k is equal to 4, that is like gives you the terms which are maximum degree of polynomial which you have is something like u cube, which is enough to give the curvature continuity. Now, let us look at mathematical definition little more closely. Suppose if I choose, let us say I am just taking an example of n is equal to 5. If I take n is equal to 5, that means I have 6 control points. This is true with both Bezier as well as B-spline. If I take let us say n is equal to 5, the definition of the Bezier curve which is obtained is defined, say completely defined, because I have terms which are starting from 1 minus u to the power of 5. Next time I have 1 minus u to the power of 4 which is multiplied by u. So, slowly the 1 minus u's power decreases and u's power increases from 0 to 5, and I have a binomial coefficients. So, this is phi c 0 which is 1, phi c 1 is 5, phi c 2 is 10, okay. Phi c 3 is also 10, phi c 4 is 5, and then phi c 5 is 1, and these are multiplied by the respective x coordinates. So, this is completely defined between u is equal to 0 to 1. Let us look at the definition for a non-uniform B-spline curve. Here not only I am giving the control points, but I have to also supply what is the k which I have selected. Let us say I have selected k is equal to 3, which gives me a slope continuity. Then we have seen in our earlier equation that I have the B-spline basis function which is multiplied with the coordinates. So, if I look at this, since k is equal to 3, this is n03, n13, n23, n33, and it goes all the way up to n53, which are what you call as a B-spline basis functions. We will see soon how these what is the mathematical definition of these B-spline basis functions, but for the time being we can only know that that you have to evaluate these B-spline basis functions in order to define the curve completely. And u also we know, that is n minus k plus 2, n here is 5, k is 3. So, there are curve will consist of 4 segments, 0 to 1, 1 to 2, 2 to 3 and 3 to 4. Now, what happens like when I give a definition like this? For example, if I take u is equal to 0 to 1, there is one portion of the curve which has u is equal to 0 to 1. So, what are the control points? How many control points will influence? 3 control points. Okay. What are those? x0, x1 and x2. So, naturally for the range u is equal to 0 to 1, all these B-spline basis functions, that is n33, n43, n53 will automatically become 0. Next time when I select u is equal to 1 to 2, n03 will be 0. This is non-zero, non-zero and non-zero, whereas n43 and n53 will be zeros. So, these n's, what you call as the basis functions, are defined in such a manner that the definition itself includes which will be 0 or which will be non-zero depending on the k value which is selected for a particular curve. Now, if I look at, let us say, if I try to elaborate, for example, for the same definition which I have chosen for non-uniform B-spline curve, where n is equal to 5 and k is equal to 3, okay. I have basically written down the equations, the parametric equations for the individual segments. Earlier the definition was a common. Now, if I see u is equal to 0 to 1, we know that 3 control points affect, others are 0. So, I can eliminate them and I have the coefficients which are like basically the terms like 1 minus u square, 0.5 u, etc. So, the curve, the 4 segments of the curve which will be obtained can be directly written in terms of equations. Okay. These have been basically written based on the definition which will discuss for the n value. So, I have the 4 segment 0 to 1, 1 to 2, 2 to 3 and 3 to 4 also tells which portion of the curve is influenced by which of the control points. Now, if I choose for example k is equal to 4, then I will have a different equation which will have terms x0, x1, x2 as well as x3, and all these values will change. So, I have a different you can say functions which will define when the k is equal to 4. And if I want to plot the curve also, suppose if I want to display the curve, for display purpose I want to plot the curve, or I have to take, let us say, a cutting tool along this particular curve. If I want to evaluate number of points on the curve, then you need to use different equations for the different segments of the curve. Okay. Like when I code it as a program, I have to have a different cases. If u is equal to 0 to 1, then there is a particular equation which is used. If it is u is equal to 1 to 2, then I have another equation which is defining. Now, these equations are derived in such a manner that you do not have to worry about the continuity, it is a part of a definition. So, the slope continuity will be automatically met if I go through this kind of a definition. So, let us look at some of the properties of this particular curve before going for mathematical definition. The curve is C k minus 2 continuous, this we have already seen. Whatever is the k, minus 2 will be the continuity requirements which will be there, and the curve is made up of n minus k plus 2, this also we have seen. Once I know the n and k, I know what are the segments, and only k control points affect any segment of the curve, that also we have seen, and a given control point affects 1, 2 or k curve segments depending on where they are located. Towards the ends, like suppose if I have a B-spline curve which is defined by 100 control points, which is okay, or let us say 101 control points, 0 to 100, your n is equal to 100. What happens is the only influences, that means only non-uniformity which you have is only for the first 2 segments and the last 2 segments, because the first control point affects only the first one, second control point affects first and second, the third will affect the next 3. So, that continues till you reach the other end, where I have again the non uniformity which is coming into picture. In between, all the other control points are like have the same influence. Okay. That means they would be influencing k curve segment. If k is equal to 3, they will be influencing the 3 curve segments which they have. So, that is another important you can say a property of this particular curve. Now, what is the input which I will give in order to define a B-spline curve is whatever are the control points, just like we define the when I define a Bezier curve, this is the same. If I have a cubic Bezier curve, I give 4 control points. Here whatever are the n points which you are trying to define, and you also define what is the order of the curve, which is by giving the value of k, which is an additional input given to a B-spline curve. Now, let us look at how are these basis functions are defined. Okay. The expression looks little complicated, but it is not as complicated as it looks. Any particular value of a basis function Nik is given by a mathematical expression which is this. Suppose we have taken earlier an example of n is equal to 5 and k is equal to 3. So, what are the n values which I need to evaluate? So, I need n03, I need n13, I need n23, n43, all the way up to n53. So, I need to evaluate 6 n values in order to completely define the curve. If suppose if I select let us say k is equal to 4, then it is different. I would be interested in getting let us say n04, n14, n24 which are different functions. So, given let us say a value of k, that means which is an input, and the number of points, I know what are the n values which I have to find out. And in order to find out let us say a value of Nik, I have an expression. This finding Nik requires finding the value of Nik minus 1. Suppose if I take for example n03, k is equal to 3, if I want to find out n03, then I should know what is n02, okay, that should be evaluated first. So, this is a recursive function. In order to evaluate this, I require this. In order to evaluate this, I may require some other function. So, this is a recursive function, and we know that recursive functions can be very easily implemented, particularly when it comes to a programming. So, that is one reason you can say that B-spline curve is a purely you can say evolved out of the availability of computers. Okay. Otherwise, the mathematical calculation or manual calculations would have been more difficult for different situations. And another thing which uses is all these are functions of u. Okay. This is a function of u, and you also see that there is another term which is coming in the equation, which are t's. Okay. These t's are called as basically the not vectors, which are shown here, and the number of t's which one has to evaluate is 0 to n plus k. Like if I take an example of n is equal to 5 and k is equal to 3, which we have been using. So, I have to evaluate all the t values first, which goes from 0 to 8, and that means I have t0, t1, t2, t3 all the way up to t8, and in order to define the t's, I have 3 expressions. Whether a given value of I is less than k, I have one definition. If it is between k and n, I have another definition, and if it is greater than n, then I have a third expression. So, n is an input, k is an input. Given the n and k, I can always calculate what are the t's using an expression like this. So, this is not a difficult thing. So, once I know the t's, whenever a ti is required, I can always use that in an expression which is there. Now, whenever I am evaluating this recursive expression, as I am going let us say one down below, like in order to evaluate let us say n03, I require n02, and similarly at some stage I should also know where the recursion should terminate. So, in order to terminate you have a equation. Okay. So, this is basically the equation which is used to define or to terminate this recursive function. That means, if nik is equal to 1 if it is between this, otherwise it is 0. Now, the whole definition is given in such a manner, like we were discussing about what we call as a non-uniformity of B-spline. In order to define, make it non-uniform, the definition becomes little more complex, because you have to choose the knot vectors, or the knot vectors have to be defined in such a manner that the influence is different at the ends than those at the middle. Okay. In order to basically do that, we have a situation, or we end up with an expression which is this is basically given by Debour, a person. So, this is also called as a Debur's expression for a B-spline, which is this thing. Now, let us just look at a simple example. For example, if I have n is equal to 5 and k is equal to 3, which is this thing. So, we know that the knot values go from 0 to n plus k here is 8. If I substitute in the previous expression which we have seen, I can obtain all the knot values which are this. If you see here, these are zeros at the ends, because k is equal to 3, and these are 4 values, all are 4s, the other 3 endpoints, and in between you have it is increasing in the ascending order. So, the knot vector automatically come up in a order which is required for a non-uniform B-spline curve definition. And if I go back and try to evaluate those recursive expressions, I can always say, suppose if I want my first expression n03, then I should know what is n21. Like, for example, this automatically becomes 0 for that particular thing, and you have what is called as n21 which is required, which is what is shown here. So, I need to evaluate n21 again going back recursively. If I want to evaluate n13, then I have to evaluate n21 and n31 which are the expressions. So, given this mathematical definition, it is possible to completely define the B-spline curve, satisfying all the requirements which we have seen in the properties which is there. Now, I will not go into the derivation of this expression, it is actually quite lengthy, maybe I require about 3 classes to just derive this particular expression if I want to go for this. Okay. And most of the CAD/CAM books also they do not do it. Okay. If you probably look into a books like Theory of Splines, then probably you may find basically a derivation for this, but the definition basically evolves out of the properties which we have been discussing. So, this is just an example of how to evaluate a B-spline curve, and a better way to do is to write a program for a B-spline curve rather than sitting and doing the calculations. If you really see why this is also required, suppose if I am plotting a B-spline curve, I have to evaluate, let us say if I am plotting a curve between, let us say u is equal to 2 and u is equal to 3, I may take small increments of u, and for every increment I may evaluate the expression. So, it requires lot of manual calculation if I do not use, let us say, programming in order to plot or use this. Now, before let us say I go to the next part of the curve, let me just go back and look at the basis functions. Okay. Like we have been discussing about the basis functions which we have used, okay, what we call as n03 or n13 or n23 which we have been using. The same things have been plotted. Okay. Do not worry about r is another this thing variable which is used to define this. Let us look at the first basis function, okay. That is how does this look. So, what is shown here which goes from, let us say, which goes all the way up to a value which is u is equal to 1 up to here is the first basis function. The second basis function which is shown here is this, which goes between the parameters range u is equal to 0 to 2, and then this is the a third basis function which you are seeing here. Now, how do I interpret, like these are the basis functions which are actually plotted. Now, how do I interpret here is, suppose if I take u is equal to 0, if I take u is equal to 0, then what is the value? I have only this which is non-zero, okay, only that means the entire thing is defined by the first basis function, which becomes value equal to 1, that means curve passes through the first point. Now, if I take, let us say, any value between u is equal to 0, let us say I take u is equal to 0.5, what are the curve segments which are influencing? So, I have 3 which are coming into this thing, and if I really add up all of them, like this value which is shown here and this value and the 3 values, they all are equal to 1. Like if you remember, we have seen this property as far as Bezier functions is concerned. If I add up all the basis function values at any particular u value, they add to 1. The same property is valid for B-splines too. At any particular point 5, if you see that I have 1, 2, 3 which are influencing, so that means the corresponding x values are multiplied by a factor which is different at different values of u. Once I go to, let us say, closer to u is equal to 1, let us say if I take u is equal to 0.9, what you see is that the influence of this has become much less, whereas the influence of other functions have increased, and I have a value which is like basically the weightages of these values which are used x0, x1, x2 is changing continuously as I go from one end to another. Let us say I come back to somewhere here, what happens? Some of the earlier functions have no influence, like the first basis function which I am using has no influence in this, second also has no influence, only thing is the values like third, fourth and fifth have some influence when it comes to here. As I move, the same curve continues, okay, the same curve continues to the other end. Here you have only taken a few points, that means n is which has been taken is only for a few points, you see like this, otherwise the curve continuously moves along this. So, what you see here, this one, the middle one, which what is the significance of the middle one is that this is basically influencing the 3 segments, isn't it? What are those? U is equal to 0 to 1, u is equal to 1 to 2 and u is equal to 2 to 3. Whereas, if I look at this, an earlier segment, it is influencing only 2 and this one is influencing only 1. So, this particular function which is influencing the 3 continuously repeats. Suppose if I take, let us say, 100 points, how does the, like all the basis functions look is that first and the next one will be different, all other will be a uniform functions till I reach the other end, where I have again which are basically a mirror of this. So, I have these functions, this is basically a mirror of this, this is some kind of a mirror, this is actually symmetric about the u and this function actually repeats. If I use, if suppose if I take let us say a B-spline definition where I forget about these end basis functions and use only the common B-spline basis function which is defined in the middle, okay, that is the common which is repeated for most of the points. If I choose that and try to define a B-spline curve, that is called as a uniform B-spline curve. Like we defined, we said there is a non-uniform B-spline curve, that is because if I look at these functions, they are different at the ends compared to the middle. Middle one is, suppose if the middle one is repeated for all the cases from let us say starting point to the end point, take the same function as this, then I also get a curve which is a uniform B-spline curve, and in that case the curve does not pass through the starting and end points. Okay. So, I get a curve which starts somewhere and ends somewhere, does not pass through the this thing. So, since it does not pass through, usually the starting and end point passing through a specific point is a more common requirement for design and manufacturing applications. People like non-uniform B-spline version is more commonly used than the uniform one. Now, let us come back to this. if I have understood B-spline curves, then I have understood NURBS too. What is put here is basically a definition of a B-spline curve, which we have been discussing all the time. So, I have 0 to n, I know how to evaluate ni values using a recursive function, and I have the values which are xi, and I also know what is the range. Now, a NURBS curve is basically a modification, a rational version of a B-spline curve. So, the NURBS actually stands for non-uniform rational B-splines. You know what are non-uniform B-splines? So, if I make it rational, I have a non-uniform rational B-spline version. What is done in this is, if I compare this expression with this, I have the same NIK basis function which is used here too. Same points are also used. You are actually multiplying with another scalar value, a number. So, how many h values are there? As many control points. So, every control point is given a weightage, okay, which is basically what you call as a h. So, if I give a different weightages, presently in a non-uniform B-spline curve, what you do is that you give equal weightage to all the points. But suppose if I want to influence, I want that, let us say, a third control point should have maximum influence on the curve. I will give a very high value for the associate a weight with this particular control point and multiply by that. What you see here is basically a fraction of that. In the sense, suppose if I am giving, let us say, weightages like 1, 2, 3, 4, then you are actually dividing 1 with the summation of all the 1, 2, 3, 4. So, you have a larger fraction which is coming up as a part of this. Now, if give all the h values are 1, then this is nothing but a non-uniform B-spline curve. If I give a different values of h, then you have non-uniform rational B-spline curve which comes. Now, what is the effect of that? Suppose instead of giving, let us say, weightage of 1, which is to that, suppose I give, let us say, weightage of 1 here and weightage of 100 to the second control point, then the curve will be pulled more towards that particular point. So, curve, instead of, let us say, being away from this, you will see that the curve has very, like it is passing through a point which is very close to this particular thing. If I give, let us say, weightage as a infinity, the curve must pass through that particular point too. It can be made to do that. So, by influencing, one of the ways to basically say this is, like you have a something like a spring which is attached to this, you are only varying, let us say, the stiffness of that particular spring. Stiffer the spring, the curve will be pulled more towards that particular point. If I have a very stiff spring, then it passes through a almost close to that particular point, which is a case with that. Now, what is the basic, let us say, a beauty of this particular curve is, we can see later that if I want to, we have seen the example of approximating, let us say, a Bezier curve, approximating a circular arc using a Bezier curve, it is not possible to do that. Whereas, if I take a NURBS and vary the weightages, I can define a NURBS curve which is an exact, you can say, there is a, which can be exactly used to model a circular arc. Not only circular arc, it can be used to model a straight line when the points are coplanar, collinear, when it can be made to model conics, parabola, hyperbola and ellipse by changing the weightages. Since, and we know that B-spline is a subset of this, if I choose k is equal to n, I can also reduce B-spline curve to a Bezier curve. Okay. Since all the curves which we have, and we know that any of the Bezier curves can be represented as a Hermite curve, and accordingly that also we have seen. So, a NURBS curve is enough to represent most of the other versions, because of its you can say a universality, or it is some kind of a superset of all the curves. for most of the CAD/CAM applications, this has been selected as a standard curve. Okay, like when the standards were developed for representing curves and surfaces, if different people use different forms, you may have a problem. So, if everybody uses, let us say, a NURBS form, I have some kind of a universality. So, that is the reason why NURBS is so popular, which is shown here. So, what we will see next is basically take up this NURBS curve and try to see how this can be used to represent other curves and also extend it to surfaces. The same definitions which we have seen, the Hermite curves, B-spline and the NURBS, can be extended to the surfaces, which is very trivial. In fact, you do not require much of discussion as far as that is concerned. So, I will just stop it here, and if you have any questions, you can ask.
Weightage for control points given by basis function. So
no, here
the need to give additional weightage.
Additional weightage is by giving additional weightages, you are actually getting a family of curves. For example, if I take a B-spline curve, if I give the control points and the value of k, the curve is uniquely defined. There is no multiplicity as far as that is concerned. But if I take, for example, NURBS, by default, by giving the weightages as same, that is 1, then you are getting the B-spline curve. But if I, by changing the weightages, I am getting a different curve. So, you are actually representing a family of curves using the NURBS, and this variation can be used to represent, let us say, a class of curves. Like there are many situations where I want a constraint. For example, I want to define a B-spline curve with a given control points, and also k is defined, but I want this curve to pass through a specific point. How do you do that? Once you give a control points and k, the curve cannot be made to pass through unless it is by default it is passing through. But now, if I have a weightages, I will try to manipulate these weightages such that the curve can be made to pass through this. So, even if I have additional constraints, I can impose and satisfy more requirements which are used. So, that is why when we say that it can be used to represent, or it can be used to represent most of the known forms like circle, etc., that is because you are making use of this option which is given by the weightages of a NURBS curve. Any other question? I think the best way to learn NURBS curve is to write a program to plot it. Okay. So, if I have written, let us say, a program to plot a NURBS curve, that means I have understood most of it. Otherwise, theoretically it looks simple, but once you start writing a program, then you will know that it requires quite a lengthy program in order to do that. Okay, then I will stop it here, and we will take up some aspects of NURBS curve followed by the surfaces in our